Hello students, welcome to the lecture series of M.Sc. Part 1 Semester 1st, the mathematical methods in the physics. Okay, this is the second lecture of this lecture series. So last lecture we had talked about the Cartesian form of the complex numbers. So in this lecture we are going to discuss polar form of the complex numbers. Okay, so let's start. This is the second form of the complex numbers, that is polar form of complex number. Okay. So in this form we can in the Cartesian form of the complex numbers, that we can written as z is equal to x plus I into y. Okay, so this x and y, that is a coordinate in the Cartesian systems. Okay, so we rewrite in the polar form this complex numbers we want into the polar form. So for that I am using here the transformation equation that gives the relation between the Cartesian to the polar coordinates. Okay, so first I draw here the Argon diagrams. So in the Argon diagram we consider the two axes. One is a real axis, that is x, okay, and another that is imaginary axis, that is y. Okay, so complex numbers that is associated with the points p is a function of the x and y. Okay, so this is the origins. If I draw the lines from the origin to p, so this lines has a magnitude that is r. Okay, and it's making the angle theta between the real axis and this OP lines. Okay, so this is a theta. So now here we get our triangles. If we apply the cos theta here for the triangle, okay, for the triangles, that is XOP is equal to theta. So if you apply cos theta is equal to what? This is adjacent side, this is the opposite side, and this is the hypotenuse. Okay, so cos theta is equal to, it is adjacent divided by hypotenuse. Okay, so this adjacent is equal to x and this hypotenuse is equal to r. So x by r. Okay, so from this we can find the transformation equation, that is x is equal to r cos theta. Okay, this equation is called the transformation equation that gives the relation between the Cartesian to the polar. Okay, this x is in the Cartesian, this is a Cartesian coordinate, and this r, that is a polar coordinates. Okay, so similarly if we consider the sin theta, okay, so sin theta is equal to opposite divided by hypotenuse. So opposite side is this one, so that is parallel to the imaginary axis. So imaginary axis is what? Y. Okay, so y by r. So y is equal to r sin theta. Okay, so these two equations that give the relation between the Cartesian coordinate to the polar coordinates. Okay, so the r and theta, that is the polar coordinates. Okay, so this r and theta, it is a polar coordinate. Okay, and the x and y, that is a Cartesian coordinates. Okay, so this z is equal to x plus I. If we rewrite in the term of the polar coordinates, so let's if you substitute x is equal to what? R cos theta, and y is equal to what? R sin theta. So z is equal to, you got here R cos theta plus I r sin theta. Okay, So this is a if we take the r is common in r into r into cos theta plus I sin theta. Okay, so this is form of the complex number is called the polar or the trigonometric form of the complex numbers. Okay, this is called trigonometric form of or polar form of complex number. Okay, so this is a polar form of the complex numbers. And this is the Cartesian form of the complex numbers. So in the last lecture also we seen that the modulus of the complex number. So modulus is equal to what? Z is equal to, or mod Z is equal to under root x square plus y square for the Cartesian form of the complex number. So here we have the polar form. So for that we can rewrite is a r. Okay, so r is called modulus of complex number. R is equal to mod z, or r is equal to x square plus y square. Okay, so this is a modulus of complex number. Okay, and another, that is argument of the complex number. So for the polar forms, argument of the complex number, that is theta, is called the argument of complex number. Okay, okay, and this theta is equal to, we can write I am writing here, this theta is equal to tan inverse y by x. Okay, so this is argument of the complex number, and this is a modulus of the complex numbers. Now this theta, if z is equal to 0, then this we can't find the argument of the complex number, because if z is equal to 0 means y and x is also 0. So in the last lecture we see if z is equal to 0, then what we get, x and y, x and y is equal to 0. Okay, so for if you want this arguments, then z must be not equal to 0. This is the condition. Okay, okay, for the if you want to find the argument of the complex numbers. Okay, and another thing is that this theta can be changed. I am writing here now. This theta or arguments can change theta plus 2n pi. Okay, so if we change this theta with the 2n pi, then what we get, this complex numbers means this complex number or this cos value of this complex numbers remains unchanged. Okay, if we put the in the theta, that is plus 2n pi, so this complex number, that is z is equal to r into cos theta plus 2n pi plus I sin theta plus 2n pi. Okay, so this complex number and z is equal to r cos theta plus I sin theta. Okay, it's the same things if you find the value of the z or the magnitude of the this complex number. Okay, so this is the two things. One is this condition, that is z is equal not is equal to 0, then we can find the argument of the complex number. And second one is theta is equal, if we change with the 2 theta plus 2 n phi, then this complex number remain unchanged. Okay, or value of the complex is unchanged. Okay. So this is about the polar form of the complex numbers. Now third form, that is the exponential form of the complex number. Okay, so let's see the third exponential form of the complex number. So we know the Euler formula, right? By using Euler formula, or before that we know the Maclaurin series. Okay, that is by first according to Maclaurin series. So we know the expansions of e power n is equal to 1 plus n by 1 factorial plus n square by 2 factorial plus n3 by 3 factorial and so on. Okay, and also for the cos theta, here just I am replace this n is equal to I theta. Okay, so what we get, the e raised to I theta is equal to 1 plus I theta divided by 1 factorial plus bracket I theta whole square divided by 2 factorial, and the third term, that fourth term, that is I into theta cube divided by 3 factorial and so on. Okay, this is by the Maclaurin series. And also for the cos theta is equal to what, or series of the cos theta, that is cos theta is equal to, so 1 minus if we consider 1 minus theta square by 2 factorial plus theta power 4 by 4 factorial and so on. Okay, this is a series for the cos theta. And if we can rewrite this cos theta is equal to 1 plus I, here I am writing the I. Okay, so I square is equal to minus 1, so that's why here is a plus. Okay, so that is a 2 factorial, and fourth term, third term, that is I into theta power 4, that is 4 factorial. So here I power 4, that is equal to plus. Okay, so this is for the cos theta. And third case or the third series, that is for the sin theta. So sin theta is equal to 1 minus theta cube by 3 factorial plus theta 5 by theta power 5 is equal to 5 factorial. Okay, so let me check first series. Okay, so if we multiply I to the sin theta, if we multiply I sin theta, then what you get, I plus 3 factorial plus I into theta power 5 by 5 factorial. Okay, so this I into sin theta and this cos theta, if we add, then what we get, cos theta plus I sin theta is equal to what, this series. Okay, one plus I sin theta. Here is a theta, here is a theta. Okay, so let me clear first. Here is a theta. Okay, so what we get, the 1 plus I theta divided by 1 factor plus I theta whole square divided by 2 factor plus I theta cube 3 factorial and so on. Okay, so this is we can call cos theta plus I sin theta is equal to e raised to I theta. Okay, so this is Euler formula. Okay, so now for the exponential form of the complex numbers, using this formula, cos theta plus I sin theta is equal to e raised to I theta. Okay, this is the Euler formula. So by using this formula, we can find the exponential form of the complex numbers. Okay, so you see this. Okay, now by so e raised to I theta is equal to cos theta plus I sin theta. Okay, so this is Euler formula, and we know the polar form of the complex number. Polar form of complex number that is z is equal to r into cos theta plus I sin theta. Okay, so these terms, if we can replace with the e raised to I theta, so that is r into e raised to I theta. Okay, z is equal to e raised to I theta. So this is polar form of the complex number. This is, sorry, exponential form of the complex number. Okay, so for the now let's see the algebra of this complex number, of this exponential form of the complex number. So here, if we see the multiplications of two complex number, that is in the form of the exponential. Okay, so that is z1 is equal to r1 e raised to I theta 1 and z2 is equal to r2 e raised to I theta 2. So for the multiplication, z is equal to z1 into z2. So if you write this r1 e raised to I theta 1 bracket into r1 e raised to I theta, sorry, r2 e raised to I theta 2. So this r is a modulus of the complex number, and this theta that is the argument of the complex number. Okay, so r1 dot r1s we can write like this, and e raised to I theta 1 plus theta 2. Okay, so this is the product of this two complex numbers. Now if we represent this in the Argon diagrams, let's see in the Argon diagram, this product of the two complex numbers, this is the real axis and this is imaginary. So suppose this Z1 this theta 1, that is the argument of the Z1, and R1, that is the modulus of the Z1s. Okay, so we can write here, this is OP. Okay, OP, that is R1, OQ, that is R2, a modulus of the Z2, and this theta 2, that is a argument of the Z2. Okay, so product of this two complex number, this is Z2 and this is for the Z1. Okay, so product of these two complex numbers, you get like this, ON. So modulus, that is R1 into R2 of this two complex numbers. Okay, product of these two complex numbers, and the argument, that is theta 1 plus theta 2. Okay, so that is angle between the XON. Okay, this is X, and here for the arguments, that is theta 1 is angle between the XOP triangle, and here theta 2, that is triangle between the XOQ. Okay, like this. So this angle, that is theta 1 plus theta 2. Theta 1 plus theta 2. Okay, and this is a magnitude, that is ON is equal to R1 into R2. Okay, so this is representation of the product of the two complex numbers. Okay, now division of the two complex number. So it's complex number. Okay, second one. So same, these two complex number we consider Z1 equal to R1 into e raised to I theta 1, and Z2 is equal to R2 into e raised to I theta 2. Okay, so Z is equal to Z1 by Z2, and Z1 is equal to what? R1 e raised to I theta 1 divided by R2 for the Z2 is equal to what? R2 e raised to I theta 2. Okay, so you can write R1 divided by R2 e raised to I theta 1 minus theta 2. Okay, so if we represent this by the Argon diagrams, so we real and imaginary. This is theta 1. Okay. Triangles XOP, that is theta 1, and the modulus, that is R1. Okay, and another, that is, so here I write theta 2 minus theta 1. Okay, see this ON, that is making an angle theta 2 with the x-axis. Okay, and modulus, that is R2, R1 and R2. So division of these two complex number, that is we can represent with the OQ. Okay, so it's angle, making an angle that is theta 2 minus theta 1 with the x-axis. Okay, so this is representation of the division of the two complex numbers in by the Argon diagrams. Okay. So this is three form of the complex numbers, and next one, that is roots of the complex number and the power of the complex numbers. Okay, so let's see the root of the complex number and the power of the complex number. Okay, so first one, that is power of complex number, and then we discuss the root of the complex number. Okay, so power of the complex number, here we consider polar form of the complex number, that is z is equal to r into cos theta plus I sin theta. Bracket completes. So by the Muir's theorem, we can find the power of this complex numbers, that is z power n. This n is any integers. Okay, so we can write bracket r into cos theta plus I sin theta power n. Okay, so by using the Muir's theorems, we can write this z power n is equal to r power n into cos n theta plus I sin n theta. Okay, so this is we can find the root, or sorry, power of the complex number. So this n is equal to any the integer numbers. Okay. Okay. Now next one is the roots of the complex number. Roots of complex number. Okay, so for the roots of the complex number, here I am considering the one complex number, that is alpha, and this alpha is equal to a plus ib. Okay, in the Cartesian form, this alpha is equal to a plus ib. Okay, so if you want to find the root of these complex numbers, then you consider one relations, or also for this we can rewrite in the polar forms, that is alpha is equal to r into cos phi plus I sin phi. Okay, so this r is a magnitude, and this phi, that is the phase or the argument of this complex number, that is alpha. Okay, so if you want to find the root of this alpha, I am consider one relation, that is alpha power 1 by n is equal to z. So value of or root of this alpha, that is equal to z, and we know that z is equal to what? R cos theta plus I sin theta. Okay, so this is root. So just I am rewrite alpha is equal to z power n like this. Okay, from these relations. Okay, so if alpha is equal to z power n, so we know the z power n is equal to what? R power n into cos n theta plus I sin n theta, and this theta is also changed with the theta plus 2k pi. Okay, So alpha is equal to what? R cos phi plus I sin phi is equal to z power n. So z power n is equal to what? R power n, right, into cos n theta plus I sin n theta. Okay, from the D Muir's theorems. Okay, this relation I am writing here from the D Muir's theorems. Okay, so if we compare now, here this theta phi is also changed. So let rewrite cos phi plus 2k pi okay plus sin plus I into sin phi is equal to phi plus 2k pi is equal to this r power n cos n theta plus I sin n theta. Okay, so if now compare this r with the r power n, so we can rewrite r is equal to r power n, right? So what we get, the r value of this magnitude of r, that is magnitude of the alpha, magnitude of alpha, that is r is equal to r power n, right? So and also if we compare this n theta with this phi plus 2k pi, so what we get? N theta phi plus 2k pi. So theta, that is argument of this complex numbers, so that is we can write theta is equal to phi plus 2k pi divided by n, and here we can write r is equal to r power small r is equal to capital R power 1 by r. So this is modulus and argument of this complex numbers. Okay, so this alpha we can rewrite in the term of this z we can rewrite in the term of the capital R and the phi. Okay, so what we relations alpha power 1 by n is equal to r. Okay, so that is the root of the alpha. So root of the alpha is equal to what? R z. So root of the alpha is equal to what? Z, and z is equal to, we can write r cos n theta plus I sin n theta. Okay, so from this relations we can rewrite this r is equal to what? R power capital R power 1 by n into, and this cos, here is a cos, and theta is equal to what? Phi plus 2k pi by n. Okay, so phi plus 2k pi divided by n plus I sin theta, and the theta is also I sin theta is equal to what? 2k phi plus 2k pi divided by n. Okay, so this is a root of complex numbers. Okay, okay, so let's stop here. We will discuss the next topic in the next lecture. Okay, thank you.